Okay, let's go ahead and get started. Um, so we do have a survey for you guys to fill out, midpoint course survey, guys to say whether we're doing a good job or a bad job or a mediocre job or something in between. So go ahead, fill that out. Give you 5 minutes to do that. Well, if you're not in the
I
classroom, then you can.
already did it. Is that fine?
For this course, you already did it.
For mid-course? Yeah, I did it this morning
Oh, that works.
because it was posted by Sios the Hedge.
Oh, size edge. Oh, is it? Oh, okay. Yeah, that's fine. But for those of you who did not do it, course is not split. We can go ahead and get started with the lesson, unless people feel very strongly that they need to do the form right now. We can get started and you can finish it. Oh my God, someone has thumbs up floating around their head. We can get started and then finish. You guys can finish the form after the lesson. So let us commence. Luke, I think it's you.
Hey guys, today we're learning about focal lengths. So, for review, what does it mean for rays to converge and how is that important to form an image? Like, does the image form when rays converge or diverge or both?
You can do like a ray tracing, and if it converges, it's like usually a real image. And then if it diverges, you can like trace the ray like opposite to the direction it's facing, and that's a virtual image.
Yeah, exactly. I think everyone in the chat also got that. So we have parallel beams, divergent beams, and convergent beams. And what things can we say about a real image compared to a virtual image? Other than the fact that one is usually formed by converging and the other is usually formed by diverging rays.
If anyone wants to unmute and say the answer, that's also great.
Yeah, Ethan, exactly. They can, if you put it on film, you can see it. And I'd love for you guys to turn on your cameras if you haven't already. And I'm pretty sure we already answered the second question, so yeah. So mirror and lenses. How are mirror and lenses similar, and how are they different? Yeah, so looking at all the answers in the chat, I think everyone got everything. So lenses refract, mirrors reflect. An ideal mirror is a small mirror, and an ideal lens is a thin lens. And they both form images, and they also have focal points, which we will see today. Yeah. So, right. So convex lenses converge rays and concave mirrors converge rays as well. And here's an image to summarize what we've just discussed. So now we're gonna learn about focal lengths. So a focal length, so as you can see here, when all the rays incoming to a lens are parallel, ideally they should all focus at one point called the focal point, which is right here. And the distance between the focal point and the lens is called the focal length. So why is the focal length in this lens positive while the focal length in this lens negative?
And
Yeah, if you guys want to say it out loud, definitely say it out loud.
The lenses are like different. So the
Right.
positive one is a converging lens, and then
one,
this is diverging.
Yes. So when the focal point is to the right and the rays are coming in from the left, the focal length is positive, and the opposite is true for the opposite situation. So it's negative when the focal point is to the left. So thinking about this, how would you, what kind of mirror would have a negative focal length? So when you draw a diverging mirror, what kind of mirror is it? So it's convex, right? So here are our rays, and here's the convex mirror, right? So where would the focal point be? To the right or left of the mirror? Yeah, so actually, you would think that since it's a diverging mirror, it's obviously gotta be on the focal length's gotta be on the left, like a diverging lens, right? But if you draw the rays go out like this. So then the focal point must be on the right side of the mirror. So then knowing this, is the diverging mirror, which is also convex, does it have a positive or a negative focal length? So that diverging is concave for lenses, but diverging is convex for mirrors. Exactly. So a diverging mirror or a convex mirror has a positive focal length, and a converging mirror or a concave mirror has a negative focal length. Next slide. So today we're going to be learning about the thin lens, and today we're going to learn about the thin lens and the thin lens equation right here, and we'll see a derivation soon. And what in our three variables are the object distance O, the image distance I, and the focal length F. And in this image, M equals -2. So given that you have the image distance, the object's distance, and the focal length, how could you find the magnification, which is M?
But more rather than just like as a formula, can anyone like explain why that's how you get the magnification? Because image over object, yeah, that's true. But like how do we end up with that result? We do math. This is true. See, the equation is so as a rule of thumb in physics, if your answer is just equation, it's it's probably a correct answer, but maybe not the best answer, right? You want to
Mm-hmm.
have an abstract logical explanation for everything that happens.
So when you look at an object, like think of a microscope. When you turn the magnification to two times to like 500 times the magnification, right? Does that mean what does that do to your image as you see it? What does 500 times mean? Exactly, it's 500 times bigger. So magnification is comparing what two things? Yeah, the size or the height of the object. So, and it's only negative because it's flipped. And as you notice here, the m equals -2, that's really similar to the ratio of the image distance and the object distance, right? And that's because of similar triangles. And therefore, we can write m equals -I over O, which is true because of similar triangles, comparing this height and this height. So next slide.
Sorry, one second.
O
Nothing.
is not necessarily proportional to I. The, I mean, if you hold a magnification constant, then O is proportional to I, but normally people aren't asking you to hold a magnification constant. They're usually asking you to modify the object distance or the image distance without changing the lens. So you should be normally you just want to think about how O and I relate to F. So power, you can also think of focal length in terms of power, which is just the reciprocal of the focal length. And a lens with high power has what kind of focal length? High or low focal length?
Low.
Exactly, because it focuses the object really, it focuses the rays really close, which is why the focal length is low. Next slide. Yeah, so in summary, focal length is the distance light converges to. Magnification is the negative of the image. Sorry, magnification is the image height over object height, which is also equal to the negative of the image distance over object distance. And power is the reciprocal of focal length. Next slide.
All right, so let's take a look at this reference diagram right here. Then we have all the stuff that that we have learned now in this lesson. So as we have just mentioned, power is the reciprocal of focal length in diopters, very useful units. And then the lateral magnification, how much your image increases in size, is measured by the negative the image distance over the object distance, which is with triangles, you can prove that that's equal to h prime, which is the new height of the image, over h, which is the original height of the image. And then the Gaussian form of the equation, which is just one form of it, is 1 over O plus 1 over I is equal to 1 over F. But on the last slide, I don't know if you saw at the bottom right of the screen, you have x naught times xi is equal to f squared. That's another way to write this equation. It's the same thing. Just the other one lets you solve for the variables a lot easier. So we're going to be using the Gaussian form a lot more than the Newtonian form, although Newtonian form also does work. All right, so let's take a look at a practice problem and think about this for a second. So without consulting the formula shown that we just talked about, does increasing the object distance make the image distance bigger or smaller or the same? Assuming that the focal length is the same. Sorry about that. All right, so if we can actually look at a simulation I have pulled up online, if I can share screen. Here, let me share this tab here. Here, so let's take a look at what happens when we decrease the object distance. We can see here that the image distance increases a lot when we decrease the object distance. Here, let me show the principal rays instead, so that they go through the focal points, just like we've learned to ray trace. You can see that when we decrease the object distance, we increase the image distance. Let me go back to the slides for a second. All right, next question. Give me a second. All right, there we go. Everyone should be able to see my screen. Now, how would increasing the focal length impact the image distance, assuming that the object distance stays the same? Decrease, we see decrease, decrease. Okay, so let's look at what happens. Switch out of this. There we go. Let's look at what happens when we increase the focal length. The radius, we'll see the relationship between the radius of curvature and the focal length later. But here, let's put our image back here. When we increase this, we increase the image distance. And when we think about the ray tracing part of it, it's actually, you can think of this logically. If we have this point going farther here, then we'll need to bend this one more, and thus it's going to cross the rays farther to the right. Does that make sense? When we increase the point, we see that the ray has to bend a little bit more to the right, and thus is going to cross all the rays a little bit farther. Does that make sense to everyone? Perfect. All right, since we're going to be using simulation, I'm going to enter full screen. But now, how would increasing the object distance increase the image magnification? If we increase the object distance. So if we think about the diagram, right? When we increase the object distance, the image is going to get smaller. And we can think about it in terms of ray tracing, because this line has to be less of a sharp slope. And thus this line is going to be higher upwards. And thus it's going to cross all the rays, a higher point under the axis, meaning that the magnification is going to be lower. But you can think about it in terms of all the rays at once. If you decrease if you increase the object distance, you're more far away. And the closer you get to infinity, the closer you get to the rays converging at the focal point. So it makes sense that when you increase the object distance, it gets closer to the focal point. So this is just what we were saying, an intuition for all of them. And we got all the answers here. A lesser object distance always increases the image distance. A greater focal length increases the image distance. And a greater object distance decreases the object magnification. Let's send it off.
Any questions about what we've talked about so far?
Now, are there any questions? All right, let's move on then.
All right, so now we're gonna derive that equation. Fear not, this derivation is not nearly as involved. Certainly no calculus, not really any trigonometry either. It's basically just similar triangles. And it's very important, I think, to see, because if you don't know where the equations that you're using are coming from, then you're just using equations and you're not really doing science at that point, I think. You're no better than ChatGPT. So you really got to understand where these things come from to sink your teeth into the physics. So let's start. So we're looking at this below situation right here. We have an object that goes from point A to point B, and the fact that you are comparable to ChatGPT. Okay, so what's going on? Why is there no hell no? Sorry, I'm not trying to. I don't want to make anyone get lost. I'm gonna go nice and slow here. So what's the issue? Okay. Yeah, if there is an issue at any point, if you don't understand, just speak up. I can back up a little. But okay. So we have an object that goes from point A to point B on the left. Okay. And that object produces an image that goes from point, maybe use the annotate, maybe that'll be good. How do I annotate? Okay. It's not,
Maybe you have to share screen. I can stop sharing. You can go back to sharing your screen yourself.
it's fine. It's fine. Okay, I'll just talk. So the image goes from
I'll
point
try
C
to
to
do my best.
point, the image goes from point C to point D, and the object goes from point A to point B, like Arthur just drew. We're gonna focus on two primary rays here. This top solid pink ray That's our first principal ray, right? That goes into our lens directly, straight on, and then refracts through the focal point at F and creates our image. And our second ray, which Arthur just drew over in blue, is going to go straight through the center of our lens and remain straight. That's how the refraction works there. And you can prove that to yourself with Snell's law on your own, but we're going to accept that as true because we know that's true from Snell's law. So notice how our object distance goes from A to O. Our image distance goes from O to C, and our focal length goes from O to F. These are the facts of the situation. This is what we're starting out with. We've defined a situation with certain truths and assumptions, and we want to create more truths that we can extrapolate from here, that we can extract from here. Any questions so far about what's going on? Okay. Oh, I did figure out how to draw. Okay. So we're gonna make two similar triangles to start out. This is with that top pink ray. The triangle OEF, that left triangle, is similar to triangle CFD. Similar, you guys should probably remember from geometry, hopefully, does not mean they're the same triangle. It means that they have the same angles on the inside. And because they have the same angles on the inside, that means the ratio of the lengths of their sides are the same, right? Can we all agree on that? Do we all understand why that's true? Proportional side lengths. Yep. Okay. So that means that the ratio of CD to EO, which is going to be our bottom right triangle from CD, which is going to be the height of these triangles, CD to EO, that ratio should be equal to CF to OF. That's our length of these triangles. This is just a product of the similarity of these two triangles. We know the length OF is equal to the focal length F, and we know the length CF is equal to the image distance DI minus F. That's because we defined those things earlier, and those lengths of these triangles happen to line up with that. So CD over EO is equal to DI minus F over F, which equals DI over F minus 1. This is our first equation, the red equation. I'm going to use red for it in the future as well, and this is the first thing that we're defining to begin with. What's complicated, Ethan? What can we explain here? The minus 1, so that comes from when we just divide out this fraction. Di minus f over f is just di minus f over f, and f over f is 1. So di minus f over 1 minus 1. It's the same thing from that bottom right to the far bottom right. It's just dividing out the f from the right side of the fraction.
Should I write it out?
Yeah, sure.
Here, di minus f over f is equal to di over f minus f over f, which in turn is equal to di over f minus 1 here. So we're just splitting the fraction into two, and then one of them is equal to 1.
Yep.
So that's how we get here from this.
So are we all good up to there? If anyone's lost, like privately message me if you don't want to like feel embarrassed that you're lost, because you shouldn't be embarrassed, first of
Yeah.
all, but even if you are, we're here.
There are no bad questions.
Yeah.
If you're wondering something, someone else is probably wondering that same thing. So you're just doing them a favor.
Okay, then we'll move on. So we've established that first equation. Now we're going to move on to our second equation. We're going to do the exact same thing. We're going to set up two similar triangles, but now these are from that second ray, the dashed pink line that we drew initially, and we do the exact same thing. The length CD on the far right is divided by the length AB on the far left. Our two heights are equal to the length OC and AO. That's actually the same as our magnification formula that we showed earlier, but we're just going to use it to our advantage because it's from similar triangles. And that's equal to DI over DO. However, we know that the height EO is the same as the height AB. So CD over AB is the same as CD over EO. The height AB is the same as the height EO because that is what we defined initially. That is a fact that we have assumed in this problem. Okay? Because remember that point E came from drawing a ray straight from B into the lens. So it makes sense that it would be the same height, AB and EO. So therefore, CD over EO is equal to DI over DO because OC was DI and AO was DO. Do we understand this equation? Yeah. So this triangle is our second ray that we always draw. Whenever you do a ray tracing situation, you draw a ray from your top of your image, from your object through the center of your lens to see where the image is formed, okay? We know the image is formed here, we assumed that, and we're drawing a ray from our object through the center of the lens to our image. By doing so, we create two triangles with that middle line that divides our lens in half. And those two triangles are made with the same angles. If you remember from geometry, whenever you have a line, whenever you have two lines like this, the angles on um, the angle right here and the angle right here are the same angles. Okay? So since these are the same angles, this length AB, that's a transversal, yeah. That length AB and this length CD that I just circled in red are the AB, or sorry, CD divided by AB is the same as, let me use a different color here. I'll use dark blue. AO divided by, sorry, CO divided by AO. CD over AB, it, CD over AB is the same as OC over AO. They are proportional to each other. And we also know that DI is the same as OC and DO is the same as AO. That's what we assumed from the beginning. So CD over AB equals DI over DO. And finally, AB is the same as the length of EO. That's another thing that we assumed from the beginning. So we just substitute in that length EO for AB to get our second equation here. CD over EO equals DI over DO. Does this make more sense?
Yeah.
Okay. Move on. Just shout out if you have a question. So now what we're left with is just cleaning it up. So remember this top right equation. My this equation right here that I just circled in yellow. That's from the two slides ago. That's our red equation. This equation right here, also circled in yellow, is our blue equation that we got from the last slide. They both say CD over EO equals something. So if their left-hand sides are the same, their right-hand side should also be the same. Does that make sense? If x equals y and y equals z, then x equals z, right? So CD over EO equals DI over F minus 1, which equals DI over O. So we move down to the bottom right over, oh sorry, bottom left over here and set them equal to each other. Does that make sense why we did that? And how
Yes.
we were able to do that? Transitive property, that's what that's called. Yeah. Okay. So then, given this DI over DO equals DI over F minus 1, we divide both sides by DI. So you can see on the left side, I still wrote out the DI in the denominator. On the right side, I divided out DI over here. So DI over F divided by DI is 1 over F. And then minus 1 divided by DI is minus 1 over DI. The, la the last thing we do is cancel out these guys. And we're left with 1 over DO equals 1 over F minus 1 over DI. Add 1 over DI to both sides, and you get our final equation. Do we understand the process of how we did that? The transitive property is just saying, like, if one thing equals X and another thing equals X, then those two things are equal to each other. If I have 5 apples, and actually, that's a bad example. X equals Y and Y equals Z, then X equals Z. I don't really, I can't think of a good example off the top of my head for some reason, but yeah, what Arthur said. Why did we divide DI? To simplify. We didn't really have to. Like, ultimately, the equation at the top that's circled in green is the same as the equation at the bottom that's circled in green, and you could use both equivalently. But I think we'd agree that the equation at the bottom looks a little prettier than the equation at the top. It's a lot simpler, right? And our goal is to have the simplest possible equations.
Like imagine if you were solving for DI. Would you really
Mm.
want to have like two places where you have to figure out what DI is? Now you would rather have it all in one place and dividing it by DI on both sides of the equation. It allows us to isolate it so that we can plug it in or plug in every other variable and solve for DI. So it's just a simpler equation overall.
Yeah. Well put. Does anyone want me to just review that one more time before we move on to the final activity? Just go through it quickly. Or do we all feel pretty confident about how that worked? That this is the attendance code. Yes. Oh, that's the wrong link.
So I thought it said loser four. That's funny.
Okay. Arthur, can you go back to the first bit of the derivation?
Mm-hmm. Let me see. Right here.
Okay.
Correct.
Yeah. So just brief review. We started by defining our two primary rays that we're interested in. One of them goes straight from AB into the lens and then refracts and goes through the focal length to form the image. The other one goes from our object through the lens, center of the lens, to the image. It goes straight. That's just because of Snell's law, because of how refraction works. So we're going to say the distance of the object from our lens is DO. The distance of the image from our lens is DI. The focal length of the lens is F. And the rest of these points are as defined. These are our assumptions of the problem, and we're gonna accept all these things as facts. We're trying to make new facts based on these facts. What can we extrapolate from here? So can you next slide?
Mhm.
So the first thing we do is take that top ray and look at the similar triangles that it forms with this middle axis. We call that the optical axis, by the way. I don't think I've used that term before, but this middle line that goes through the center of the lens is our optical axis. So we form a ray from that pink line with our optical axis to get two similar triangles. Now, because these are similar triangles, because this angle right here in green is the same as this angle right here in green, because of the transversal as geometry, we know that this line CD circled in green divided by the length of this line EO circled in green is the same as this line CF circled in red divided by this line OF circled in red. The ratio of the green to green is the same as the ratio of red to red. This is because they are similar triangles, that's because of geometry. We know that OF is equal to F. That's defined right here. That's the red line. I don't need to do any extra drawing. Uh, yeah, I think someone just wanted to review it, so that's fine. But so OF is the same as the focal length. OC is the same as the image distance. And so that's how we get to CD over EO equals DI over F minus 1. Go to the next slide. We do the exact same thing with another set of two triangles. To get that, I'm not going to go through all the details for this one, just for the sake of time. CD over EO equals DI over DO. These steps are detailed right here, and steps are detailed right there, and hopefully If you go through the recording afterwards, you can further clarify for yourselves. But CD over E equals DI over DO. Next slide, please. And finally, we set the red equation from 2 slides ago equal to the blue equation from last slide to get DI over F minus 1 equals DI over DO. And with some simple algebra, we just simplify the two to get 1 over TO plus 1 over DI equals 1 over F. So that's our thin lens equation. Once again, if this is a little too fast for you, the recording will be out there and you can review it then, and of course, send us emails with any questions.
All right, so let's get to a little activity that we've prepared. I'm going to share screen, and this is going to be some practice for some ray tracing and then using our golden equation to find out all of the intricacies of the system, most notably the image distance and the image height, depending on the type of lens. So what we're going to do is we're going to go into breakout rooms and probably teams of 4, 5 other instructors. Any opinions? What we're going to do is we're going to have a couple scenarios with one lens, one object. And what you guys are going to do is grab your lenses or mirrors, place them on the optical axis, draw some rays to wherever it's supposed to go, and then calculate the image distance, calculate the magnification, and then you're going to tell us the image type and the image orientation. So this should be pretty fun. Just these are free for you to adjust any way that you want. You can make the lenses bigger to better fit your diagrams, or smaller if you need to. You're going to place these dots where the focal points are supposed to be. That's also for you to determine. And then finally, you're going to place your image with an appropriate size.
This is the homework. This is just an activity for
Yeah,
us
this
to
is
do.
just an activity. The distances and the rays do not have to be perfect. This is diagram, like this is just diagramming. Like it doesn't have to be perfectly calculated, etc. Neither do the rays. They just have to be reasonable and appropriate for the scenario. Like if it's a virtual image, your image should not be on the other side. It's probably going to be on the side that the virtual image would like actually be on. It's the if it's within the object distance, then it should be on the right side. Say this is a mirror, it should be on here, right? If it's a concave lens, the image is going to be within the object and the lens. This is appropriate. Anywhere here is appropriate, depending on your ray tracing. This is not, and this is not. But the specifics on the distances are for you to determine. Okay. Could we split up into breakout rooms, Sean?
Yeah, so do you want like each group to work on one of the slides? Is that what you're saying?
I was thinking we could have everyone work on as many slides as possible.
Okay, so
Just
like
going over it as a group, and then once you're all done with that slide, just move on. That was what I was
okay,
thinking,
so
but we can do either.
each group has their own copy of the whole slideshow.
Mhm.
Okay, sure. Let me make the breakout rooms.
I'm gonna post a link to the slideshow in the Google Classroom, and then you guys can grab it, make a copy, and then share the link to the chat for your breakout rooms.
Should we have groups of 3 or 4?
I think either is fine. I think 4 is a good. Actually, how many of us are there in this meeting? 30. So let's make groups of 3, 10 groups of 3. Do your best to work through as many of these as possible, but make sure you understand everything and that you do it correctly.
So go ahead and join the breakout room invite that you should have just gotten.
Oh wait, did we include hosts? Okay.
Oh, I don't know how to. I thought it. I mean, you guys are co-hosts, right? I shouldn't have auto. I'm not in.
Yeah.
Well, that's fine.
Uh, maybe you should join group 8 or 10.
Yeah.
Wait, Arthur's with. Okay, I'm gonna join room 10 because Arthur is with someone in room 6.
Yeah. Hey everyone, we're about to end the meeting. It's 4. We'll definitely do more of this activity in the future though. So yeah.
Do we have to finish this and submit this somewhere, or is it just like an activity?
Nothing to submit. It's just an interactive activity that we wanted to. I spent too much time on the derivation, unfortunately. It
Okay.
was just a fun activity though. We'll do more of it.
Yep. We can either, Ishan, do you think we should continue this like another class or?
Yeah, for sure.
Okay, so we'll just work on it next time. Just keep in mind who your partners are so that we can put everyone in the same breakout rooms again.